In this presentation, we're going to learn how to fit a data set to a straight line, y equals to mx plus b. As an example for that, we're going to assume that we bought 100 oranges and we stored them in a refrigerator in our restaurant, a refrigerator basically. And we monitored the use of these oranges over a 3 weeks period. And this was the data we obtained. At day 0, we had 100 oranges, and then after 3 days, this number went back down to 80. After 7 days, we had only 55 oranges left in the refrigerator. In 2 weeks, 14 days, 35 oranges left, and finally, after 3 weeks, none of the oranges left. So this is our raw data that we collected from this simple experiment. So in order for us to process the data, the first thing to do is to calculate the averages, which is the sum of all the numbers divided by the total number of observations. So for time, we had average of 9 days, and for the number of oranges, we have an average of 54 oranges. And then we calculated differences. For time, every observation minus the mean of the time and squared it, and then we sum up all these together to end up with 290 days square. We repeated that for the number of oranges, and then the last one, the differences for time and oranges together. So we took all these differences pairwise and multiplied them together, and we summed them to end up with negative 1315. So notice here we have 3 differences, sums, that we will be utilizing to calculate parameters for the linear equation. So now we're going to calculate the slope and the y-intercept as parameters for this linear equation. The slope is calculated for the time in oranges divided for time, and that is negative 1315 divided by 290, which gives me negative 4.53 oranges per day. So basically we are consuming 4.5 oranges every day. The y-intercept, we're going to use the averages for the number of oranges and the time in the equation, and I put the equation here in this slide. By using this equation, we end up with 94.77 oranges. Now, please note here that this number in reality should have been 100, but our data is not perfectly linear. So this number is used in the algebra to predict the number of oranges that are left in the refrigerator at given time. The next parameter to calculate is the correlation coefficient, and correlation coefficient is important to give us the strength of the relationship that exists in between the response and the predictor variable. The response here is the number of oranges left in the refrigerator, and the predictor variable here is the time. So again, we're using those differences sum in the calculation, and I put the equation here. Notice here the raised to the power of half is simply taking the square root of the terms. If you do the algebra, you end up with negative 0.9911. The closer the value here to negative 1 or plus 1, the stronger is the association between the independent variable time and the response, which is the number of oranges left in the refrigerator. Please note here that a strong correlation does not mean necessarily causation. Finally, we write the equation that we have obtained. Number of oranges left equals to the slope, negative 4.53 multiplied by the time plus the y-intercept, 94.77. So say I want to predict the number of oranges left at day 9 in the refrigerator. I just replace the time by 9 and calculate the algebra here and give me 54 oranges left in the refrigerator. This is just to predict the number of oranges that would be there in the refrigerator when I need them. Of course, this is used as a prediction tool for the future use. So every time I'm gonna buy 100 oranges and place them in a refrigerator, I can go back to this equation and calculate based on this data how many oranges would be there for me at a given time.